Hi, in this video we'll go over the solutions for this week's section worksheet on Bayes nets, independence, inference, and sampling. Let's start with the first question on d-separation. D-separation is an algorithm that helps us answer the following query on a Bayes net. Are two random variables, x and y, conditionally independent given some evidence variable set z? To answer this query, we do the following process here. First, we shade all the evidence variables, that is, all the variables in the set z. Then, we consider each undirected acyclic path between the two query variables. For each path, we figure out if the path is active or not. A path is active if all the triples along the path are active. And to determine whether a triple is active or not, we use the following chart shown here. There are three categories of triples. The first one on the top is called the causal chain, and the causal chain triple is active if the middle node is unobserved, and the triple is inactive if the middle node is observed. The second category of triples is called the common cause triple, which, like the causal chain, is active if the middle node is unobserved and inactive if the middle node is observed. The third category of triples is called the common effect triple, and this one is different. The triple is active if the middle node is observed. However, if the middle node is unobserved, we first have to check if any descendants from the middle node are observed. If there exists a descendant that is observed, the triple is active, which is shown by this configuration shown here. Otherwise, if no descendants are observed, then the triple is inactive. Okay, so we look at all triples along the path, and we say that a path is active if all the triples along the path are active. If we find at least one triple along the path that is inactive, we say that the path is inactive. If all the paths between the two query variables are inactive, we return that it's guaranteed that they are conditionally independent given your evidence. Otherwise, if we find at least one path that is active, we return not guaranteed. Okay, so on to the problem. We're given this Bayes net with 7 variables shown here, and for our reference, the categorization of active and inactive triples are shown here. We're given 7 queries to answer, and we'll use d-separation to find the answers to these queries. So let's start by looking at the first query. Are u and x independent? There's no evidence here, so we don't need to shade anything in the Bayes net. We look at all undirected acyclic paths from u to x, and there's only one path, and that's the path utx. On this path, there's one triple, which is utx itself, and let's determine whether this triple is active or not. This triple is a common cause triple with the middle node unobserved, and so we have this one in this box. This is an active triple, so this triple is active. And since all the triples along this path are active, this path is active. Since we have found at least one active path, we return that it's not guaranteed that u and x are independent. Next, we have the query, are u and x independent given t? We first shade the evidence variable, which is t, and we look at all undirected acyclic paths from u to x. Again, there's only one path, it's the same path as in part 1, and so the path is utx. In this path, there's only one triple, and so we have to find what kind of triple it is. This is a common cause triple with the middle node observed, and so it looks like this. This triple is inactive, and so since we have found one inactive triple along this path, this whole path is inactive. Since all the paths from u to x are inactive, we can return that it's guaranteed that u and x are independent given t. The third query asks us, are v and w conditionally independent given y? Let's first shade our evidence variable y, and let's look at all undirected acyclic paths between v and w. There are only two paths here. The first path is vtw, and the second path is vyw. Let's look at the first path first. So for the path vtw, there's only one triple here, and let's look at what this triple is. So VTW is a common cause triple with the middle node unobserved, and so it's an active triple. Since all triples along this path are active, this whole path is active. And so we can actually stop here, because once we know that we have found at least one active path, V and W are not guaranteed to be conditionally independent given Y. But let's do the analysis for the other path as well. For the path VYW, again, there's only one triple along this path. This triple VYW is a common effect triple with the middle node observed. So it's this triple here. This triple is also active, and so since all triples along this path are active, this whole path is active. And since we have found at least one active path, it's not guaranteed that V and W are conditionally independent given Y. The fourth query asks us, are V and W conditionally independent given T? Let's first shade our evidence variable T, and let's look at all the paths between V and W. There are two such paths. They're the exact same paths that we had in part 3, and so let's write that down. We have the first path as VTW and the second path as VYW. Let's analyze the first path first. Along this path there's one triple, VTW. VTW is a common cause triple with the middle node observed, and so this is an inactive triple. Since we have found at least one inactive triple along this path is inactive. Let's take a look at the second path, VYW. There's one triple. So we have the triple VYW, that's a triple with the middle node unobserved. So we have to be a little careful here. We first have to check if there's any descendants of Y that are observed. In effect, luckily Y doesn't have any descendants, so we're fine. And so we can conclude that this is a common effect triple with the middle node unobserved and none of its descendants observed, and so it's an inactive triple. And since we have found at least one inactive triple along this path, this whole path is inactive. Because all paths are inactive, we can return that it's guaranteed that V and W are conditionally independent given T. The fifth query asks, are T and Y conditionally independent given V? Let's first shade our evidence variable V, and then let's look at all the undirected acyclic paths from T to Y. There are two such paths. We have the path TVY and the path TWY. Let's look at the first path first. There's one triple along this path, and TVY, that's a causal chain triple with the middle node observed. And so this is an inactive triple. Since we have found at least one inactive triple along this path is inactive. Let's look at the second path, which again only has one triple, TWY. TWY, that's a causal chain triple with the middle node unobserved. And so this triple is active. Since all the triples along this path are active, this path is active. And so since we have found at least one active path between T and Y, it's not guaranteed that T and Y are conditionally independent given V. For the sixth query, we're asked, are Y and Z conditionally independent given W? So let's first shade our evidence variable W, and then let's look at all the undirected acyclic paths between Y and Z. There are two paths we need to consider. The first path, let's say it's Y, V, T, X, Z, and the second path we have Y, W, T, X, Z. On the first path, there are three triples, YVT, VTX, and TXZ. YVT, this is a causal chain triple with the middle node unobserved, and so it's an active triple. VTX is a common cause triple with the middle node unobserved, and so it is also active. And TXZ, again, it's a causal chain triple with the middle node unobserved, so this is also an active triple. Because all triples along this path are active, this whole path is active. And so since we have already found at least one active path between Y and Z, we can already say that it's not guaranteed that Y and Z are conditionally independent given W. Now, just for practice, we can do the other path as well. Along this path, there are three triples: YWT, WTX, and TXZ. Let's first just look at YWT. This triple is a causal chain triple with the middle node observed, and so this triple already is inactive. Because we have found at least one inactive triple along this path, this whole path is inactive, but still holds that since we found at least one active path between y and z, it's not guaranteed that y and z are conditionally independent given w. Alright, so let's look at our final query. Are y and z conditionally independent given t? Let's first shade our evidence variable t, then let's look at all the paths between y and z. Those are going to be the exact same paths as in part 6, so let's just copy those over. YVTXZ and YWTXZ. Let's analyze the first path first. There are three triples along this path. Again, YVT, VTX, and TXZ. So here, YVT is a causal chain triple with the middle node unobserved, and so it's an active triple. VTX, that's a common cause triple with the middle node observed, and so this is an inactive triple. And TXZ is a causal chain triple with the middle node unobserved, and so it's also an active triple. Because we have found at least one inactive triple along this path is inactive. Let's analyze the second path, YWTXZ. Again, there are three triples along this path: YWT, WTX, and TXZ. Well, first we already know TXZ is an active triple because of same as here. YWT, that's also a causal chain triple with the middle node unobserved, and so YWT is active. For WTX, again, we have a common cause triple with the middle node observed, and so this triple is inactive. Because we have found at least one inactive triple along this path is inactive, and because all paths connecting y and z are inactive, it's guaranteed to be the case that y and z are conditionally independent given t. And that's it for d-separation. Next, let's look into performing inference queries on a base net. In this problem, we're given the same base net shown here, and we're asked to perform variable elimination to compute the conditional probability of y given plus z. And so in variable elimination, we start with all of the initial factors being the conditional probability tables in the base net, instantiated with the evidence, which is plus z. And so that's why we have 7 factors here, where each factor corresponds to one of the tables in the base net. We are going to go over all of our hidden variables, and just as a reminder, a hidden variable is just a variable that's neither a query variable or an evidence variable. And so in this base net, we have all the variables that aren't y or z. We go over all the hidden variables, so let's start by looking at part A, where we go over the hidden variable x. For this hidden variable x, we look at all factors involving x, which are p of x given t and p of plus z given x. We join those factors together by multiplying them, and then we sum over all possible instantiations of x and eliminate x out of the term. So this leaves us with a factor that involves everything other than x, which is plus z and t. Plus z goes in front of the conditioning bar because it appears in the front of one of the factors that we joined on, and t only appears in the back of the conditioning bar, and so it stays in the back of the conditioning bar. Kind of the other case that's missing here is what if you have a variable that appears in the front of a factor and then sometimes in the back of another factor? Well, in this case, the variable will go to the front of the conditioning bar. So let's keep these rules in mind when we generate our next factors. Once we have this new factor, we add this factor back into our list of factors to consider. And so these are our new factors that we have. Note that p of x given t and p of plus z given x are removed, and we have this new factor that enters into our list of factors. So let's continue the variable elimination process. For part C, we are joining and eliminating on the hidden variable t, and so we first go through our list of factors and look at which factors involve t. That's p of t, p of u given t, p of v given t, p of w given t, and f1 of plus z given t. So when we join on them, we multiply these 5 terms together, and so let's write p of t times p of u given t times p of v given t times p of w given t times f1 of plus z given t. And the reasoning why I wrote a lowercase t is because I'm going to eliminate t off the bat. So we sum over all t of the joined factor that we have here. This creates a new factor f2, which involves everything here that's not t. So we have u, v, w, and plus z. So each one of these terms appears in the front of the conditioning bar for the corresponding factor, and so they're all going to be in the front of the conditioning bar in the resultant factor. So we end up with the factor f2 of u, v, w, and plus z. So let's remove these from our list of factors, and we're left with the factors p of y given v, w, because that wasn't used, and this new factor f2 of u, v, w, and plus z. For part E, we are joining and eliminating on the hidden variable u. We find all factors that involve u. In this case, it's just f2 of u, v, w, and plus z. We join on this factor. Joining on one factor just gives us the factor itself. And so we eliminate u by summing over all instantiations of u of f2 of u, v, w, and plus z. This creates a new factor that involves all our variables except for u, and so we have v, w, and plus z. All of these variables appears before the conditioning bar, and so they will stay before the conditioning bar, and so we have f3 of v, w, and plus z. With regards to the factors we have left, we remove f2 and we add in f3, and we're left with 2 factors, p of y given vw, which we didn't use, and f3 of v, w, and plus z. For part G, we are joining and eliminating on the hidden variable v. So we look at which factors involve v. In this case, both of these factors involve v. And so we join on these factors and we eliminate v. We sum over v of the probability of y given little v, w, f3, v, w, plus z. And this creates a new factor, f4. f4 involves everything that these 2 factors involve other than v, which are y, w, and plus z. So we need to figure out where these 3 variables go. Well, y and plus z, those are easy because they only ever appear in the front of the conditioning bar, and so they will stay in front of the conditioning bar in f4. For w, w appears in the front of the conditioning bar for the factor f3, and in the back of the conditioning bar for the factor p of y given vw. In this case, w will continue to stay in front of the conditioning bar, and so we put w here. We have joined on these 2 factors and removed them from consideration, so we're only left with one factor, f4 of y plus z and w. There's one more hidden variable to join and eliminate on, and that's w. So we look at which factors involve w. In this case, we only have one factor that involves w. Joining on this factor gives us the factor itself. We will eliminate w by summing over all instantiations little w of f4 of y plus z and little w. This creates a new factor, f5, that involves everything but w, which is y and plus z, both of which will go in the front of the conditioning bar since it only appears in the front of the conditioning bar. And so we remove f4 from our list of factors and add back in f5. We're left with the factor f5 of y plus z. For part K, we're asked how we can determine the table p of y given plus z. After eliminating all of our hidden variables, our factor list should only contain factors with variables that are either our query variables or our evidence variables. As the final steps of variable elimination, if there's more than one factor left, we join on the remaining factors and then normalize. But since we only have one factor left in our list, we can just normalize this factor directly. The normalization step requires us to divide each entry in f5 of y plus z by the sum of all entries in f5. Well, the sum of all entries, remember there's one row per value of y, and so we should sum over all possible values of y of f5 of little y plus z. And this is how we get p of y given plus z, and the process for doing this is called normalization. For part L, we're asked to think about the size of the largest factor, assuming that the variables are all binary, meaning that they take on two values. Because the variables take on two values each, the size of the factor depends on the number of unobserved variables the factor contains. So let's go back to our factors that we generated and see which one has the most unobserved variables. When we first created f1, f1 contains one unobserved variable, which is t. So we have 1 here. When we create the factor f2, f2 contains three unobserved variables, u, v, and w. f3 contains two unobserved variables, v and w. f4 contains two unobserved variables, y and w. And f5 contains one unobserved variable, y. And so f2 is the largest, so we'll write f2 of u, v, w, and plus z. This is the largest factor. It has three unobserved variables. And since each variable is binary, this means that the factor contains 8 rows. For part M, we're asked to see if we can think about a better elimination ordering, one which generates smaller largest factors. So you want to reduce the size of the largest factor that gets generated. Let's think about this. The initial ordering of hidden variables was x, t, u, v, and w. When we joined and summed over x, we created a factor f1 of plus z given t. This factor is okay because it has one unobserved variable, and so it's relatively small. So we can keep x in our ordering. Let's think about t. When we joined and summed on t, we created a factor f2 involving u, v, w, and plus z. Now this factor contains three unobserved variables and is actually the largest factor that we generated. So we want to reduce this factor size down. Is there another variable that we can eliminate earlier to try to reduce this factor size? Well, yes, let's think about u. So when we join on u, we look at all of the factors involving u, which is just going to be p of u given t. Summing over this factor, we get a sum over little u of p of u given t. This creates a factor, and this factor looks as follows. It should only involve t, and since t comes after the conditioning bar in this factor, it should also come after the conditioning bar in the resultant factor. This factor looks a bit weird, and there's a reasoning for this. So let's take a look at this factor very closely. For any value of t that we put in, the value in this table is a sum over u of p of u given t equals the value of t that we chose. And since we know that p of u given t equals any t is a valid distribution, it must sum to 1. And so this value actually sums to 1 for any value of t we put in. So this table here, it just contains one row for each value of t, and the value of that row is 1. A table of 1s is not entirely meaningful, and so we can actually discard this factor. That means that now, when we join and sum over t after eliminating u, let's write that down. So we have u, and then we're eliminating t. We'll create a new factor that looks like f2 prime of v, w, and plus z, because we no longer include the factor of p of u given t. And so let's include v and w to finish this ordering up. This ordering will contain a largest factor size of 2 unobserved variables, which means that the largest factor generated has 4 rows, assuming that the variables are binary. It also turns out that other answers could exist as well, so let me make a note of that. So if you got a different ordering that has the largest factor size of 2 unobserved variables, that's great. And this concludes variable elimination. On to the last question on sampling. In this question, we're given a basenet shown here. This basenet has 4 variables, W1, W2, I1, and I2. The intuition behind these random variables is W1 and W2 are modeling the weather, whether it's sunny or rainy, and I1 and I2 is modeling whether or not you ate ice cream on days 1 and 2. So we modeled this kind of weather ice cream example with this basenet, and we have the following probability tables. We have P of W1 at this node here, that's this table here, P of W2 given W1 at this node, that's this table here, and for the ice cream nodes, we're assuming both of these nodes follow the distribution P of I given W. And the model for that is here. So we generate 10 samples shown here, and for the first part, we're asked to approximate the probability that W2 equals R. The intuitive approach here is to find the fraction of samples that have W2 equals R. So the equation for doing that is the count of samples with W2 equals R divided by the count of all samples. So let's write that down. So how many samples have W2 equals R? That would be this one here, this one here, this one, this one, and this one. So I count 5. We have 5 samples with W2 equals R, and we have 10 samples in total, and so the approximation is 1/2. For part 2, we're asked to cross off all samples rejected by rejection sampling if we're computing P of W2 given that I1 equals T and I2 equals F. In rejection sampling, when we generate a sample and come across an evidence variable, if the value we generate for that evidence variable does not match the evidence value set in the query, we immediately reject that sample. So at the end, the only samples that we should generate for this example are the samples that have I1 equals T and I2 equals F. And any other sample should not have been generated. So the only samples that we should have left are this sample, because it has I1 equals T and I2 equals F, and this sample here, because it has I1 equals T and I2 equals F. And the remaining 8 should have been crossed out, because it should have been rejected by rejection sampling. The intuition here is that the samples that we crossed out here are not useful in answering our query, since we are given that I1 equals T and I2 equals F. For part 3, we are again given the query P of W2 given I1 equals T and I2 equals F, and we are also given the following 6 samples and asked to perform likelihood weighting sampling. Since rejection sampling might reject a lot of samples if the evidence is not likely, in likelihood weighting we force the evidence variables to take on the values specified by the query here, so that we don't have to waste a lot of time rejecting samples. By doing so, we only sample at the non-evidence variables. This creates a problem. To account for the fact that we are no longer sampling over the joint distribution, since we are skipping over sampling at the evidence variables, we need to keep track of a weight for each sample, and the weight will be the product of the entries of the conditional probability tables that are stored at the evidence variables. So let's write that as a side note here. We have the weight of a sample is going to be, given that we have evidence variables, and let's enumerate them from E1 to EK, so let's assume we have K evidence variables. The weight is going to be the product from I equals 1 to K of the probability of EI given the parents of EI. We know the specific instantiations of the parents of EI, since they would have either been other evidence variables that already have their values, or they would have been non-evidence variables that we have already sampled. So to calculate the weight of the first sample, STRF, we again look at our query here. Our query has 2 evidence variables, I1 equals T and I2 equals F. So we would expect our weight to be a product of 2 different values. The first term is going to look like P of I1 equals T, given that W1 equals S. So where do we get this term from? Well, we have to look at the probability table stored at the evidence variable I1, which is going to be the probability of I1 given W1. This explains why this term looks like this. I1 equals true based on this value in the sample here, and W1 equals S based on this value in the sample here. And for the second term, we have the probability of I2 equals F, given that W2 equals R. Again, the reasoning here is we look at the probability table stored at I2, which is probability of I2 given W2, and the value of I2 is going to be F, and the value of W2 is going to be R from this sample. Looking up values in this table up here, the probability that I1 equals T, given that W1 equals S, that's going to be this term up here, so that's 0.9. And the probability that I2 equals F, given that W2 equals R, that's going to be the last term down here, which is 0.8. And so multiplying these two numbers together, we get that the weight is 0.72. For part 4, we have to calculate the estimate of P of W2, given that I1 equals T and I2 equals F. To find this value, we first have to look at all the weights of all the samples, so we need to create a table for this. We'll follow a similar procedure as part 3 to compute the weights, and doing so you should end up with the following weights shown in this table here. Now let's see how to calculate P of W2 equals sun, given that I1 equals T and I2 equals F. So this value is going to be equal to the sum of all weights of the samples where W2 equals sun divided by the total sum of all weights. Let's write this down here. The samples with W2 equals sun are the last 3 samples shown here, and the total weight of these samples is going to be 0.09 plus 0.09 plus 0.02. That's a total of 0.2, and the sum of all weights, when you add all of these weights together, is 1.8. And so our estimate for P of W2 equals sun, given that I1 equals T and I2 equals F, is going to be 1/9. For the probability that W2 equals rain, given that I1 equals T and I2 equals F, well, since we know that this forms a distribution, it's just going to be 1 minus 1/9, which is going to be 8/9. And this concludes sampling.